On the morning of January 5, 1943, in the vast waters near Guadalcanal, none of the sailors aboard the light cruiser USS Helena could have imagined they were about to witness one of the most pivotal moments of World War II. The tropical sky was heavy and gray, low clouds drifting lazily as waves lapped against the hull. Suddenly, the radar picked up a formation of Japanese aircraft approaching. Alarms blared across the decks, gunners rushed to their stations, barrels trained skyward, waiting for the order to fire. The first plane to enter range was an Aichi D-3A Val, the Imperial Japanese Navy's main dive bomber. It plunged from more than 2,000 meters, nose down toward the Helena, wings folding in for another precise strike as it had hundreds of times before. But this time, something extraordinary happened. Just seconds after Helena's first shells were fired, a blinding flash erupted in midair. The Val disintegrated, not from a direct hit, but because one shell exploded near it. The crew stood stunned. It wasn't luck or a miracle, but the first combat success of one of the greatest technological inventions in wartime history, the proximity fuse, also known as the VT fuse. Before this, every anti-aircraft round relied on a mechanical time fuse set by hand to detonate after an estimated interval. Gunners had to guess the target's altitude, speed, and direction, adjusting so the shell would explode roughly near the plane. A tiny miscalculation, just a few milliseconds, meant the shell would burst too early or too late, letting the aircraft slip by unharmed. In real combat, especially against fast maneuvering planes, the odds of a hit were almost zero. It took around 2,500 rounds to down a single aircraft. Anti-aircraft fire looked fierce, but was little more than a sky full of fireworks. The U.S. Navy had learned this the hard way at Pearl Harbor in 1941. Hundreds of guns fired back, yet most shells missed. Worse, delayed explosions fell back onto Honolulu, killing civilians and damaging American property. The lesson was clear. Without a technical revolution, anti-aircraft defense would remain a paper tiger. But how could a shell know when it was close enough to a target to explode? That question haunted scientists in the early war years. Amid countless proposals, one idea sounded so absurd that many dismissed it outright. Using radio waves to measure distance, like radar detecting an object. The man who made that idea real was Dr. Merle Tuve, a physicist at the Carnegie Institution in Washington, D.C. He realized that if one could build a tiny radio transmitter and receiver small enough to fit in a shell's nose, it could sense when it neared an aircraft. When the reflected signal grew strong, meaning the distance was small enough, the circuit would trigger detonation instantly. That was the essence of the proximity fuse. In theory, it was simple. In practice, nearly impossible. A 5-inch, 127-millimeter naval shell endured over 20,000 Gs of acceleration when fired, enough to crush nearly all electronics of the era. Vacuum tubes, the heart of every radio device, were fragile and bulky. To survive, every component had to be redesigned from scratch. Miniature vacuum tubes just centimeters long, special batteries that activated only after launch, and ultra-simple yet reliable oscillator circuits. In August 1940, the U.S. Navy officially funded the project, led by the Carnegie Institution and later the Applied Physics Laboratory at APL at Johns Hopkins University. Industry giants like RCA, General Electric, and Eastman Kodak joined in, inventing entirely new ways to mass-produce compact, shock-resistant electronics. Within 2 years, what had once seemed like science fiction became reality. When the first prototypes were tested in mid-1942, the results exceeded all expectations. Shells detonated at just the right distance and altitude, so precisely that engineers had to recheck their instruments to believe it. Gone were the futile barrages. Now only a few rounds could shred an airborne target. The Navy immediately grasped the weapon's value, but also knew it had to remain utterly secret. If Germany or Japan discovered the principle, they could devise countermeasures or copy it. Thus, for an entire year, VT fuses were deployed only on Pacific Fleet ships where the risk of a dude falling into enemy hands was minimal. Then came January 5, 1943, the first real combat use. A shell from USS Helena exploded near an attacking Val, its radio sensor detecting the reflection from the aircraft's body and triggering detonation just meters away. The resulting metal cloud shredded the plane instantly. A crew officer later wrote in his log, "We'd never seen anything like it. Not a single direct hit, yet the planes blew apart as if the shells had minds of their own." Word spread quickly. By mid-1943, American fleets were increasingly equipped with VT fuse shells, and Japanese aircraft losses multiplied. Pilots whispered that the Americans now had self-aiming bullets. They weren't entirely wrong. But the true miracle lay not just in its battlefield results. It embodied the union of fundamental science, applied engineering, and large-scale industrial coordination. The proximity fuse wasn't merely a mechanical device. It symbolized a technological revolution where physics, electronics, and military strategy converged. While much of the world still relied on analog and mechanical weapons, embedding an electronic brain in a shell that could sense its target was an idea ahead of its time. That single explosion above Guadalcanal marked the dawn of smart weaponry, the moment intelligence began to enter bombs and bullets alike. From that day forward, USS Helena and other ships fought with an advantage their enemies couldn't comprehend. Each time a Japanese plane erupted without being hit directly, the secret held. Even many American gunners didn't know why their fire had suddenly become so deadly accurate. To them, it was simply better ammo. But to their commanders, it was a strategic turning point, a breakthrough that could reshape the war. And indeed, from that flash in the sky over Guadalcanal, the course of warfare changed forever. One shot, one invention had ushered in the age where human intellect began to merge with weaponry. The proximity fuse not only helped America reclaim the skies of the Pacific, but also laid the foundation for all modern guided munitions, from radar-guided missiles to precision smart bombs. When that shell burst, Helena didn't just down an airplane. It proved that human ingenuity could transcend physical limits. And in the thunder of naval guns, a new chapter in the history of military science was born. From the early decades of the 20th century, the appearance of aircraft turned the sky into a new battlefield. But anti-aircraft technology lagged far behind the rapid development of flying machines. Guns, maintenance procedures, and fire control methods had been designed for an era when aircraft were slow, flew low, and were relatively predictable. As speed, altitude, and maneuverability increased before and during World War II, the gap between detection, calculation, and the ability of anti-aircraft guns to act widened, becoming almost an unbridgeable chasm. Understanding the nature of that problem is the key to seeing why the idea of the proximity fuse was so important. A traditional anti-aircraft gun relied on a chain of 3 crucial steps: measuring the target's distance using optical devices or primitive radar, determining altitude, and predicting the target's future position to calculate how long the time fuse must count down before detonation. Performing those 3 steps in combat, when the target constantly changes speed and course, and when smoke, clouds, sun glare, or the sea's motion interfere with instruments, was nearly impossible. A gun crew might do well on a training range against a steadily moving target. At sea, facing an attacking formation, every calculation had to be made in seconds, and errors accumulated quickly. The first problem was the shell's time of flight. A 5-inch anti-aircraft shell could take 15 to 30 seconds to fly from the muzzle to the altitude band where aircraft operated. In that interval, a plane traveling at a few hundred miles per hour could move a great deal. It might climb, turn, slow, or accelerate. Thus, for a shell to detonate at the right moment, gunners and fire control had to predict precisely where the aircraft would be at that future instant, not just where it was now. That prediction depended on a chain of estimates: distance, altitude, speed, and heading, each carrying error, and each error compounding into the next step. The result was that even when measurements were acceptably accurate, the timing error for the fuse remained so large that most shells detonated in ineffective parts of the sky. The second problem was the reliability of mechanical time fuses. Fuses at the time were small clockwork devices that had to be set by hand on the ship's deck before being loaded into the gun. Under the pressures of battle, vibration, wetness, heat, and cold, and the chaos of incoming bombs, manipulating those tiny mechanisms accurately was error-prone. Many shells detonated too early, many too late, and some failed to detonate at all because of mechanical faults. The consequence was not only wasted ammunition, but also danger to civilians and friendly forces. For example, the delayed explosions that fell on Honolulu after the Pearl Harbor attack, killing civilians. The third problem was the target's maneuverability and use of concealment. In modern warfare, aircraft do not fly predictable straight lines. They evade fire, split formations, and attack from varying angles to reduce anti-aircraft effectiveness. Dive bombers could change their dive angle, speed up or slow down to upset timing calculations. Even the best radar of the era provided only a blurred picture, and fire control systems remained heavily human-dependent. Therefore, guns could only create a sea of fire, firing many rounds in the hope that some detonated near the target, instead of aiming at a specific point in the sky. From a commander's perspective, the consequence was huge expenditure of ammunition and manpower. The defended airspace was large, shipboard magazines were limited, and each gun added only a marginal defensive capability when using old technology. In a modern naval battle, with potentially large, simultaneous air attacks, rapid ammunition depletion exposed a strategic weakness.
If the enemy maintained sufficient sortie intensity, anti-aircraft defenses would quickly run out of shells. In that context, even small improvement ideas were valuable. Advances in fire control, radar, and automatic height finders increased effectiveness somewhat. However, they did not solve the core problem. The fuse timing was still set by humans, and the projectile remained unthinking. What was needed was a leap, not merely more accurate measurement, but shifting the decision of detonation timing into the shell itself, so the shell could know when it was near a target. If that could be achieved, the entire complex process would collapse into an automatic action, reducing the burden of pre-computation and manual precision. The idea of using radio waves to detect distance and set detonation timing for a fuse arose alongside radar development. Radar had shown that radio waves could detect objects at range and that return signals could indicate distance and relative velocity via Doppler effects. If a compact transmitter-receiver could be fitted into a shell's nose, it could emit pulses continually and receive reflections. When the reflected signal's strength rose sharply or a frequency shift indicated close proximity, the circuit could trigger detonation. In theory, this would allow the shell to detonate at an optimal distance automatically, regardless of how maneuverable the target was or whether the onboard timing set on the ship had been accurate. However, the technical difficulty lay in the fact that 1940s electronics were based on vacuum tubes, fragile and much larger than a shell. A conventional vacuum tube large enough to detect and amplify signals would be destroyed by the extreme acceleration in the gun barrel. Power was also problematic. How to supply energy at the right time without introducing hazards? Moreover, the circuitry had to function amid violent vibration, temperature swings, and inside a metal body spinning at high speed. Engineers realized that applying existing electronics as is would not succeed. What was required was a revolution on the spot. Miniaturize vacuum tubes, change glass and materials, design centrifugally activated batteries, and build extremely simple yet sensitive circuits capable of detecting weak reflected signals. That is precisely why the Proximity Fuse project was more than a simple technical upgrade. It presented an interdisciplinary gauntlet spanning physics, materials science, electronics engineering, and mass production. If successful, the consequences would transform air defense, from reliance on human estimates to trust in sensors in each shell. If it failed, the loss would be in effort and resources. But in wartime, the potential gain was too great not to try. So in laboratories and factories from the U.S. East Coast to university research centers, teams of physicists, engineers, and precision craftsmen took on the near-impossible task to make a shell become sensible the moment it left the muzzle. They understood they had to address not only dry physical problems, but also safety, fault control, manufacturability, and absolute secrecy against enemy espionage. It was precisely the combination of strategic urgency and technical challenge that created the environment in which an idea that once seemed crazy could become reality, and in doing so, change forever how the world viewed anti-aircraft defense and weapons design.
The idea of a fuse that could sense its target sounds simple when summarized in a few sentences, but turning that idea into a practical device embedded in the nose of an artillery shell brought an almost unimaginable chain of engineering challenges, and then, thanks to wartime pressure, enormous industrial resources, and thousands of diligent workers, became a machine that could produce millions of units per year. When war forced everything to move fast, scientists and engineers faced not only the problem of make it work, but the far harder problem of make it work after millions of firings, under extreme conditions, and be manufacturable at high reliability. One of the greatest obstacles came from the brutal acceleration a shell endures when leaving the barrel. A 5-inch shell can experience on the order of 20,000 G at firing. For a brief instant, every internal component feels forces equivalent to thousands of times its actual weight. Conventional vacuum tubes, the heart of radio receivers then, were made of thin glass and contained filaments and suspended electrodes, not only large, but extremely fragile. Ask how long a 6-inch vacuum tube weighing a few ounces would survive under thousands of times gravity, and the answer was virtually not at all. Thus, the first requirement was to redesign vacuum tubes entirely, make them smaller and mechanically hardened to an unprecedented degree. Major tube manufacturers like Sylvania and assigned research labs had to change glass formulas, add additives to increase ductility and mechanical strength, while still maintaining a vacuum inside. They not only altered the envelope material, but reworked electrode structures. Instead of using filament wires, they invented plate-like electrodes secured by spot welding so nothing could flop or break under shock. Small components had to carry loads by distributing stress rather than focusing it at a single weak point. Thousands of failed tests were recorded, tubes cracked, leads broke, contacts shifted, and each failure fed back into the next cycle of redesign and testing. Power supply was another fiendish problem. Ordinary batteries could not be made small, safe, and capable of delivering the required current for a radio circuit under firing conditions. A clever solution came from engineers at the National Bureau of Standards. A sealed glass tube containing an electrolyte arranged so that when the shell was still, the liquid did not touch the electrodes. When the shell spun up in flight, projectiles are given spin at muzzle exit, centrifugal force drove the electrolyte outward to contact thin metal plates and initiate the chemical reaction that produced voltage. In other words, the battery only turned on after the shell was spinning, a brilliant safety feature that prevented premature arming while using the projectile's own dynamics to power the circuit. The design was ingeniously simple, but mass production required artisanal skill, forming the glass tube, sealing precisely, mounting thin electrodes, and testing every cell before assembly. The antenna and transmitter-receiver circuitry also had to be miniaturized and specially designed. A loop antenna wound around the fuse body was developed to fit the cramped nose space, giving both mechanical toughness and the required radiation characteristics. Engineers selected an operating band around 70 to 90 MHz, a compromise between target reflectivity and a reasonably sized antenna. Creating a receiver with a sufficient signal-to-noise ratio, SNR, to detect weak target echoes amid electrical and mechanical noise was an achievement in itself. Amplifier stages were needed, yet had to be extremely compact and shock-resistant. Designers deliberately reduced circuit complexity, optimizing for a few core functions: transmit, receive, frequency comparison to detect Doppler, and a trigger circuit that closed when conditions were met. But a lab-viable design was not the final answer. It had to be turned into a product that could be manufactured in the millions. That task forced government and industry to reorganize supply chains. Work was parceled out to many contractors, each responsible for a segment. One firm made vacuum tubes, another batteries, another antennas, yet another handled final assembly. This raised an immensely difficult coordination problem: how to ensure parts from disparate sources matched to tolerances of thousandths of an inch, how to maintain uniform quality standards, how to keep the program secret when hundreds of factories were involved. To solve this, the Johns Hopkins Applied Physics Laboratory was set up as the technical hub. Contracts went to RCA, General Electric, Eastman Kodak, Crossley Corporation, McQuay Norris, and dozens, eventually hundreds of subcontractors. Production was organized industrially. Over 100 factories participated, with about 2,000 auxiliary suppliers.
Initial monthly targets were only tens of thousands, but wartime demand pushed numbers far higher. Goals were 40,000 fuses per day by the end of 1943 and 70,000 per day as the war continued, figures that seemed absurd for an electronic device of that era. Hitting those numbers required automating many delicate operations previously done by hand: precision cutting, drilling, micro-welding, vacuum testing, and above all, quality control. The testing regime had to ensure every fuse functioned, vacuum tubes held vacuum, circuits oscillated at specified frequencies, batteries activated with spin, and the assembled fuse survived simulated firing acceleration. Those tests demanded dedicated equipment, simulated guns, vibration rigs, and complex measurement systems, all developed in parallel with production. Secrecy was another critical element. The program was compartmentalized and run under strict security. Factories cloaked their work, workers often only assembled components without knowing the final product, and information was split among contractors. Documentation used misleading terminology, for example, calling components variable time to mask their radio nature, to prevent any revealing pattern should a part fall into enemy hands. That secrecy benefited from a bit of luck. When the Germans acquired small samples, they often disbelieved that electronics could withstand such acceleration and therefore did not devote large resources to reverse engineering them, helping keep the technology secure through much of the war. Economically and industrially, the project was a wartime lesson. Early costs per fuse were astronomical, estimated at roughly $732 in then dollars, an eye-watering sum for a single projectile. But mass production, process improvements, material optimizations, and automation drove costs down. By 1945, the unit cost was about $18. That decline reflects both economies of scale and rapid industrial learning as a vast supply chain mobilized. In total, more than 22 million fuses were produced during the war, a manufacturing achievement few scientific projects had matched in so short a time. When all these elements, ruggedized designs, spin-activated batteries, loop antennas, simple Doppler circuits, a distributed contractor network, strict quality control, and airtight secrecy were assembled, the proximity fuse became reality. It was not merely the triumph of an idea, but the triumph of organizing industrial production at scale to convert science into practical weaponry. And every fuse that left a production line thereafter carried the imprint of hundreds of hands, from design engineers to assembly workers, turning what once seemed a crazy notion into a concrete force that changed the map of war.
When the first proximity fuses left the factories and reached the sailors' hands, their impact did not emerge from a single brand battle, but from salvo after salvo, small engagements that quickly accumulated into a systemic transformation of warfare. The effect was not merely that more aircraft were shot down. It reshaped how the enemy planned attacks, forcing them to sacrifice precision and tactics, and in many cases rendering older combat doctrines obsolete. From the earliest trials, the VT fuse's effectiveness was undeniable. During a test in Chesapeake Bay, the USS Cleveland fired at drone aircraft and, using only a few dozen shells, an extraordinarily small number by previous standards, destroyed all 3 targets. This proved that a single shell could create enough shrapnel to tear through wings, fuselage, and control surfaces. In combat, this meant no longer relying on huge volumes of fire and luck. Just a few shells exploding at the right distance were enough to cripple an aircraft. In the Pacific, where the U.S. fleets constantly faced aerial attacks, that demonstration became a matter of survival.
Instead of creating random walls of flak, ships could now generate kill zones capable of destroying aircraft at safer ranges. The results were striking. Under similar conditions, VT fuses proved several times more effective than timed fuses, sometimes 3 to 7 times as effective at sea, and in some trials up to 25 times better than pre-VT performance. Ships could defend themselves more efficiently, use fewer rounds, and preserve ammunition stocks for prolonged operations. This forced the enemy to adapt. Japanese pilots, once accustomed to precise dive bombing, suddenly found their previously safe flight paths lethal. Some began attacking from higher altitudes to stay beyond VT range, but this reduced bombing accuracy. Torpedo bombers flew extremely low, trying to use sea surface reflections to trigger premature detonations, but that made them more vulnerable to defensive fire and other weapons. To avoid one danger, they had to accept another, and often a worse one: missed targets, failed attacks, and wasted sacrifices. When Japan shifted to kamikaze tactics later in the war, the VT fuse remained crucial but revealed its limits. Suicide attackers did not retreat once damaged. They pressed on even with shattered aircraft. Simply wounding them was no longer enough. Planes had to be completely destroyed at greater distances, or fire density increased to stop them earlier. In massive kamikaze assaults, U.S. ships coordinated multi-layered defenses, long-range radar fire control, 5-inch VT-fused guns, and close-range automatic weapons. Even then, some damaged kamikaze still managed to hit ships, proving that while the VT was indispensable, it was not a stand-alone solution. The fuse's impact also extended to Europe. During the defense against Germany's V-1 flying bombs, VT transformed Britain's air defense. The V-1s were fast, low-flying, and difficult to hit with timed fuses. Once Churchill approved VT use, results were immediate. Kill ratios soared within weeks. Many V-1s exploded midair before reaching London. The weapon saved entire neighborhoods and reduced pressure on fighter squadrons previously forced to chase these small but relentless threats. On land, the VT fuse's debut was devastating for German troops during the Battle of the Bulge in the winter of 1944. Initially withheld for fear of capture and reverse engineering, it was finally authorized for urgent use. The results revolutionized artillery effectiveness. Instead of exploding on impact, shells detonated in the air, scattering fragments across wide areas. A single airburst could inflict casualties over an area many times larger than a ground burst. Advancing formations were shredded. Troops suffered injuries from overhead and lateral shrapnel, turning open fields and river crossings into killing zones. Reports from Patton's forces described entire German units annihilated by such barrages, tangible proof of the fuse's battlefield power. Another crucial effect was psychological. When enemy soldiers saw shells bursting directly overhead and aircraft shredded by invisible forces, they attributed it to mystical American technology. The secrecy surrounding VT production reinforced this aura. Many believed the U.S. possessed superhuman radar-guided weapons, or intelligent shells. That misunderstanding led them to adopt suboptimal tactics, sometimes weakening their own effectiveness. In summary, the proximity fuse brought an immediate set of advantages: higher kill rates, ammunition savings, effective defense in poor visibility or at night, and reduced ship losses. It also forced the enemy to rethink tactics, choosing between precision and safety, or risking destruction to maintain attack capability. Though not a silver bullet for every threat, especially kamikaze assaults, the VT fuse marked a leap in the art of war, from reliance on luck and volume to reliance on sensors and precision. Repeated across thousands of battles, its effects drained enemy air power and reshaped the outcome of the final campaigns of World War II.
As the guns fell silent across Europe and the Pacific, people began to tally not only the planes shot down, the ships saved, or the battles turned, but also to glimpse a larger picture, a chain of strategic consequences and a deep technological legacy born from what had seemed merely a better fuse. The proximity fuse did more than bring immediate battlefield gains. It transformed how governments, militaries, and industries cooperated. It laid the groundwork for a new technical ecosystem, and it reshaped the mindset behind weapons research in the post-war era. Strategically, the VT fuse had two closely linked effects. It immediately strengthened naval and artillery defenses while exerting long-term pressure on the enemy's offensive capacity. At sea, when bombers and torpedo planes were destroyed before reaching effective range, U.S. fleets could undertake riskier operations, amphibious assaults, blockades, and major offensives with far fewer losses. On land, shells detonating in the air inflicted greater casualties and stripped attackers of terrain-based cover. The wide spread of shrapnel made older assault tactics obsolete. These changes triggered a manpower crisis for the enemy. Pilots, navigators, and soldiers were lost faster than they could be replaced, eroding long-term strategy. On a broader scale, enhanced air and artillery defense helped extend Allied offensives on favorable terms. Fewer ships lost, fewer bases destroyed, intact supply lines, all of which steadily weakened the Axis counterattack capability. Another strategic dimension lay in psychology and misinformation. The Japanese and Germans, unable to grasp the source of American anti-aircraft effectiveness, even after capturing a few samples and conducting analyses, believed the U.S. possessed an advanced beam guidance or superior radar system. This misunderstanding led to costly tactical changes, flying at suboptimal altitudes, wasting resources on countermeasures against an unknown mechanism. Even when they obtained fuses, many experts initially dismissed the idea that electronics could survive such acceleration as science fiction. Thus, the secret was preserved not only through security, but through the enemy's disbelief, a coincidence that helped the U.S. maintain its edge. In production and scientific management, the proximity fuse became a model for the state-university-industry partnership that would define major research programs of the 20th century. The Johns Hopkins Applied Physics Laboratory, electronics corporations, assembly plants, and hundreds of subcontractors formed a vast but efficient network capable of turning laboratory innovation into battlefield hardware within record time. This model was soon replicated and expanded in the Manhattan Project, missile development, and countless Cold War military and civilian programs. Beyond technical success, it taught lessons in large-scale project organization, production management, quality control, and information security under extreme time pressure. The fuse's technical achievements were inseparable from advances in miniaturization and component hardening. Ultra-small vacuum tubes surviving 20,000 Gs,
centrifugal self-activating batteries, ring antennas integrated into casings, and compact yet reliable Doppler circuits all represented breakthroughs. Precision manufacturing to thousandths of an inch and the miniaturization imperative directly paved the way for later technologies. Missile guidance systems, controlled weapon sensors, and early microelectronics. In essence, the proximity fuse was one of the earliest ancestors of ruggedized electronics, a foundation not only for defense but also for aerospace and civil aviation industries. Its industrial legacy was equally profound. Initially, each fuse cost hundreds of wartime dollars, but mass production and process optimization rapidly drove the price down to a fraction of that. This exemplified the learning by doing principle of wartime industry. As volume rose, costs, error rates, and production times fell, while reliability improved. Ultimately, over 22 million fuses were produced, a figure reflecting not only industrial capability, but the strategic scale of the program. The fuse also left a legal, policy, and ethical legacy. The early prohibition on its land use, out of fear it might be captured, followed by emergency deployment during the Battle of the Bulge, raised questions about balancing military advantage against the risk of technological compromise. After the war, as military technology became deeply entwined with civilian science, societies began confronting issues of export control, technological security, and moral responsibility in applying advanced research to warfare, questions that still resonate today. Scientifically, many physicists, engineers, and technicians from the VT program became key figures in post-war research. Their innovations in materials and precision manufacturing spread into medicine, optics, and eventually semiconductor electronics. One can trace a straight line from soldered electrodes in shock-proof vacuum tubes to the first steps in transistor and sensor technology. Wartime necessity had accelerated and standardized many of the methods that defined modern electronics. Finally, and perhaps most importantly, there was the human dimension. The proximity fuse saved lives. Fewer ships struck, fewer troops lost to air raids, safer landings and defenses, all translated into lives preserved and campaigns won with less blood. Like many military technologies, its value was measured not only in destruction, but in survival. For that reason, many scientists and soldiers alike came to see the proximity fuse as more than a technical feat. It was an invention that directly shaped both lives and strategy. In the end, the proximity fuse was a rare innovation that united three elements: immediate tactical value, rapid mass producibility, and enduring scientific industrial legacy. It changed how wars were fought, reshaped the bond between science and policy, and laid the foundation for an era where sensors, computation, and automation became inseparable from weaponry. The fuses that once burst in wartime skies did more than destroy the enemy. They shattered a technological boundary and opened the way to a new generation of post-war technology the world had never seen before.